Welcome to Deep Dive Ortho. If your professional life demands precision, real-time adaptation, and, well, operating under high-stakes conditions, and for our medical and orthopedic audience that really describes every single minute of your working day, then the technological shift we're about to explore is, I think, the foundational concept you need to master.
It really is.
We are moving well past the era of purely cognitive AI, that sort of AI brain in a vat, and we're entering the age of physical intelligence, embodied AI or EAI.
That's precisely right. So the last few years, the pursuit of truly general artificial intelligence has, largely followed two distinct developmental pathways.
Okay.
The first, which has captured most of the headlines, is what you might call the thought-first path, what we call disembodied AI.
So things like the large language models we hear so much about, GPT.
Exactly.
Yeah.
They are phenomenal knowledge engines operating entirely in the abstract realm. They reason and simulate based on vast amounts of data, language, and abstract ideas that we provided. They have immense intellectual power, but they are fundamentally divorced from the reality of physics.
So their intelligence is completely separate from gravity, from friction, from all the messy complexity of operating in a dynamic three-dimensional world.
Yep.
They can generate a perfect surgical plan on paper, but they've never actually had to deal with the feel of tissue resistance or, the wobble of an instrument.
And that's the crux of the paradigm shift. Embodied AI takes the action-first path. This is software that's inextricably integrated with the physical body, be it a complex surgical robot, an autonomous logistics unit, or an intelligent prosthetic.
Right.
The crucial point here is that intelligence doesn't just process information. It emerges directly from continuous, real-world feedback and physical interaction. It's a process of grounded learning that genuinely mirrors biological development, like the way a child learned motor skills.
I think that analogy is so helpful for understanding the core difference. It's the difference between reading a textbook on how to ride a bicycle and actually falling over 50 times until your body internalizes the complex dynamics of balance, acceleration, and how to react to the environment.
Exactly. That grounded learning is the EAI's core, its non-negotiable advantage. EAI encompasses the standard cognitive functions: perception, understanding, reasoning, planning. But it couples them tightly with physical execution.
And that's rewriting the rules for robotics.
Fundamentally, a system trying to maintain balance or execute a precise manipulation task gains far more authentic, resilient knowledge from the kinetic and tactile feedback of trying and failing in the real world than it ever could from running a billion digital simulations.
Which means it's more adaptable.
Superior adaptability and inherent resilience, yes, honed through direct physical engagement. And these are absolutely essential for high-stakes, unpredictable environments. And, what environment is more dynamic, more variable, and more unpredictable than a modern clinical or surgical theater?
That focus on physical feedback is clearly what makes EAI so relevant now to complex fields like orthopedics. And while the modern implementations feel quite futuristic, this concept actually has deep historical roots in cognitive science, doesn't it?
It does. We're certainly standing on the shoulders of decades of work. The conceptual architecture stems from early cognitive models like SOAR and ACTRE.
What were they trying to do?
Those systems were originally designed precisely to solve what was then the impossible problem. How do you bridge the gap between abstract symbolic planning, the high-level goal, perform a total hip replacement, and the continuous, overwhelming torrent of raw sensor data flowing from a physical agent that's actually operating in the world?
I see.
So the mission for this deep dive, then, is to unpack the current architectural and safety breakthroughs that are taking EAI rapidly out of the academic lab and into high-stakes healthcare environments, and what that truly means for you, the medical professional who will be collaborating with these systems.
Okay, let's unpack this shift from a purely theoretical architecture to one that's built for physical reality. If having a body changes everything, the AI system needs a structure that's capable of handling abstract thought and minute physical reality simultaneously.
Yes, that's the challenge.
We're moving beyond simple, pre-programmed automation to genuine cognitive-level collaboration. So what does that contemporary framework actually look like, and how do these systems unify perception, modeling, and ultimately decision-making?
The industry standard theoretical structure right now is known as the Dynamic Perception Task Adaptation, or DPTA framework. At its heart, you should visualize this as a continuously running, closed-loop system, a kind of perception modeling decision circuit where information flows seamlessly and rapidly between three distinct but interconnected layers.
And each layer is constantly updating.
Constantly. Each layer continuously updates the agent's understanding of the world and refines its action plan in real time.
Let's dedicate some time to those three crucial layers. Start with how the EAI system actually takes in the world.
Certainly. The foundation is the multimodal perception layer. This is where the robot aggregates and processes all its sensory inputs at the same time. This includes high-resolution vision from cameras, both RGB and depth,
And touch?
and tactile and force feedback from its grippers and end effectors, yes. Auditory cues too, listening for alarm states or unexpected noises. And crucially, data from inertial measurement units, or IMUs, that track the robot's precise position, acceleration, and orientation relative to gravity.
That sounds like a tremendous amount of data to fuse in real time, especially in a surgical environment where any kind of latency is just unacceptable.
It is, which is why simple data fusion isn't enough anymore. Modern EAI employs sophisticated mechanisms like the feature condition modal alignment, or FCMA.
XCMA.
The FCMA mechanism doesn't just average the data streams, it enhances cross-modal fusion by ensuring that the streams are aligned and semantically consistent under the specific constraints of the current task.
Okay, so what does that actually mean in practice? For our orthopedic listeners, why does that matter?
Well, let's take the example of performing a precise osteotomy. The robot is simultaneously looking at the bone, that's visual data, and feeling the resistance through the saw blade, which is tactile and force data.
Right.
If there's a sudden, unexpected change in bone density, the visual system might register a subtle shift in the field, and the force sensors register resistance chatter. The FCMA mechanism ensures that the visual structure aligns perfectly with the tactile resistance being sensed.
So it's checking that what it sees matches what it feels.
Exactly. This geometric and semantic consistency means the robot isn't reacting to visual noise or some phantom tactile feedback. It's reacting to a confirmed physical reality. This ensures the operation is safer and prevents high-risk events like microfractures or damage to adjacent soft tissue, which might happen if one sensor modality was misinterpreted.
So we've moved from basic sensor fusion to a system that actively checks for semantic consistency under the task constraints. That's a massive step up in robustness. What happens to that processed, validated information?
That moves to the heart of the system, the world modeling layer. This is the intermediate layer that acts as the cognitive mediator. You can think of it as the internal physics engine.
The physics engine. I like that.
Modern world models, informed by research architectures like Dreamer v3, do far more than just mapping the immediate environment. They comprehend the underlying real-world dynamics: friction, mass, inertia, spatial properties. Essentially, they internalize physics, which allows the system to become proactive rather than purely reactive.
So there's a sort of internal simulation running continuously in the background. What's the practical payoff of that capability?
The payoff is twofold: efficiency and safety. Because the world model can predict the consequences of potential actions before the robot physically executes them, it decouples complex learning from costly, time-consuming, and potentially dangerous physical interactions.
Can you give an example?
If a surgical robot needs to reposition a screw, it runs thousands of internal scenarios in its world model, predicting potential tool collisions or tissue stress based on its internal understanding of physics. It can simulate a high-level goal, like slightly rotate the patient's knee joint for better access, and instantly validate whether that required movement falls within the constraints of the joint and the available workspace.
So if the world model determines that the proposed rotation would lead to a cable getting snagged or an execution failure because of a structural limitation, it adjusts the plan internally before the robot ever moves an actuator.
Precisely.
That internal safety validation loop provides an essential layer of safety for tasks that simply cannot tolerate physical error.
Absolutely. This predictive capability and internal reality check drastically improve both safety and efficiency as the robot avoids dangerous or futile exploratory movements. Once the world model has validated a robust physics-compliant plan, it then has to translate that abstract concept into continuous physical action.
And that translation from high-level thought to low-level continuous motor control, that's where the real complexity lies, isn't it?
It is, and that is handled by the third layer, the policy adaptation and execution scheduling layer. This layer converts the abstract task graphs, the validated plan from the WM, into dynamic action outputs. And these outputs are incredibly diverse. They can be continuous motion commands, so precise 6D posed trajectories that define the speed and angle of every joint.
Which goes straight to the motors.
Straight to the motor controllers, yes. Or they can be high-level behavior routing directives that orchestrate sequences of mid-level skills.
It sounds like this layer acts as an air traffic controller, managing a fleet of different control methods all at once.
That's a perfect analogy. It manages an ensemble of distinct policy mechanisms. For instance, in one moment, it might use Model Predictive Control, or MPC, for smooth, continuous trajectory following, while simultaneously using reinforcement learning policies to navigate uncertainty, or maybe behavior cloning policies for rapid execution of learned specific maneuvers.
So it's choosing the best tool for the job in real time.
Yes, and the key evolution here is that the policy module is no longer a purely executive function, limited by input dimension constraints. It has evolved into a cognitive system capable of sophisticated structure modeling enhancement. It can translate high-level natural language instructions, such as "pass me the smallest retractor," into the necessary high-performance dynamic behavioral response.
That's fascinating. We often think of AI as reasoning, but EAI needs to manage the physical dexterity of its body. Does this complex, layered structure sometimes compromise speed or introduce latency?
That's a critical question, and it's why the most advanced trend right now is the development of the unified token-based architecture.
What does that mean?
Instead of maintaining distinct layers with separate interfaces, systems like Google DeepMind's Gato, or RT2, embed all input state observations from the sensors, language instructions, and behavioral tokens into a single input sequence, which is then processed within a large transformer framework.
So it's one single holistic system.
Precisely. This achieves an incredibly tight coupling. By integrating perception, prediction, and decision-making into a shared latent space, you minimize architectural complexity and dramatically increase the speed of response to instruction.
And that speed is critical for clinical deployment.
Absolutely crucial. For instance, RT2 has been shown to maintain inference latency below 150 milliseconds while achieving high accuracy. This speed ensures practical deployability even in high-demand settings like orthopedic surgery, where the robot has to react faster than human cognition to maintain safety and precision. This unified approach is truly the foundation for achieving genuine cognitive unification in a physical agent.
Right, that deep dive into the DPTA architecture paints a clear picture of how EAI systems process information and command their bodies. Now let's focus on how they acquire the necessary intelligence and dexterity.
The learning part.
Exactly. If these systems are meant to operate autonomously in dynamic hospital corridors or delicate surgical fields, they need a vast amount of grounded physical knowledge. How are we fusing the abstract semantic reasoning of multimodal large language models, MLLMs, with the critical physical grounding provided by world models? And perhaps more importantly, how are researchers managing the immense challenge of gathering enough high-quality real-world data to train them?
The synergy between MLLMs and world models is, technologically speaking, the current sweet spot. MLLMs, exemplified by research systems like Polym-E or Cogigent, bring massive high-level semantic reasoning capabilities to the table. They are excellent at interpreting complex multimodal inputs, visual, tactile, auditory, to identify objects.
For example, distinguishing between a size 10 and size 12 screw.
Precisely.
Oh.
Or inferring complex spatial relationships like the scalpel is adjacent to the sterile field, and they handle the crucial process of task decomposition.
Which is the ability to take a big, overarching goal and break it down into a logical sequence of executable steps.
Exactly. If you instruct an MLLM-based system, prepare the surgical tray for a routine knee replacement, it breaks that objective down. Identify necessary implants, locate appropriate instruments, arrange instruments in sterile sequence, and so on.
But the fundamental limitation we've always discussed is that MLLMs, trained primarily on digital knowledge, struggle intensely with the realities of physics.
They do. They might generate a plan that is semantically perfect, but physically impossible.
MLLMs are notorious for potentially hallucinating or fabricating instructions that sound plausible in language, but are physically impossible, inefficient, or outright unsafe in the real world.
That's right. A critical example in robotics is the challenge of inverse kinematics, understanding how to move the end effector without clipping the table or exceeding joint limits. An MLLM might propose a visually elegant path that the robot's physical body simply cannot execute.
And that's where the world models come in.
That is where the world models provide the necessary grounding. The WM validates the MLLM's plan against real-time environment feedback and physics-compliant dynamics.
Yeah, sure.
So the MLLM provides the semantic goal and the high-level strategy, and the WM ensures the physical feasibility and safety of every single step.
That duality ensures the system remains both intelligent and grounded. But let's get back to the data challenge. Training these models for specific high-dexterity tasks, like handling unique tissue types or using specific surgical tools, must require proprietary, highly diverse, real-world data sets that just don't exist in the public domain.
They don't.
So how is that data scarcity being mitigated at scale?
This has required a technical revolution in data collection, and the solution lies in a crucial framework developed by Google DeepMind called Otter-T Autonomous Robotic Teleoperation.
Okay.
Otter-T is specifically engineered to leverage foundation models, not just to perform tasks, but to generate the data needed for future training, scaling the deployment of operational robots in previously unseen, unstructured environments with minimal human supervision.
That sounds incredibly ambitious. If you're minimizing human supervision, how do you ensure the robot only proposes tasks that are safe and productive, especially in environments as sensitive as a hospital?
This is where Otter, or its structured multi-AI process, provides the necessary safety net. The process begins with vision language models, or VLMs, performing open vocabulary scene understanding, so essentially describing everything the robot sees in meticulous detail.
Right.
This description is then passed to a large language model, which proposes a diverse array of novel natural language instructions for the robot to attempt. But here's the critical safety mechanism. Those proposed tasks are instantly critiqued and refined by a second LLM, one guided by a specific rule-based safety protocol we call the robot constitution.
A robot constitution, so like a digital ethical guardrail. But if that constitution is defined purely by a second LLM prompt, isn't that just adding another layer of abstract bias instead of providing genuine real-world grounding? I mean, why isn't that susceptible to the same kind of hallucination we discussed earlier?
That's an excellent, incisive point. The Constitution works because it's focused not on abstract ethical theory, but on concrete, measurable embodiment rules and safety heuristics.
Okay.
These rules, which are indeed heavily inspired by Asimov's laws but are operationalized, filter out tasks that violate physical constraints. Maximum payload, arm reach limitations, forbidden object manipulation. For example, preventing the robot from attempting to lift a patient, even if it's explicitly prompted to do so by a malicious or flawed LLM instruction.
So it's a form of value alignment that anchors the LLM's creativity to the robot's physical capabilities and predetermined safety boundaries.
It is. In testing with adversarial scenes designed to trick the AI into proposing bad tasks, using this constitutional guidance led to 83% valid tasks, which contrasts dramatically with just 18% validity without it.
That is a staggering difference.
It is. The Constitution acts as the immediate hard-coded safety filter before the world model takes over for the final physics check.
And that explains how they maintain autonomy during data collection. What kind of scale has the system achieved?
The scale is transformative for robotics research. Otter-T has been deployed to orchestrate fleets of up to 20 robots simultaneously across multiple lab environments. This coordinated effort has collected over 77,000 real robot episodes and 6,650 unique language instructions.
And that in the wild data is much more valuable.
Far more diverse, visually and linguistically, than traditional lab-constrained robotics datasets. And that's vital for building generalist embodied agents capable of functioning effectively in a complex clinical environment.
Moving beyond raw data quantity, there's also the issue of learning efficiency. Traditional deep reinforcement learning, or RL, which is often used for mastering complex motor skills, is notoriously data hungry. It requires huge amounts of trial and error.
It does.
And when you're training for precision tasks like surgical manipulation, that inefficiency is just unacceptable. How is EAI tackling that time sink?
We address that data inefficiency through the Reinforcement Learning with Foundation Priors framework, or RLFP. Traditional RL starts from a blank slate, which means the robot wastes thousands of training iterations just learning basic concepts like the physics of grip strength or how to move its arm without hitting the ceiling.
So instead of learning from zero, the robot starts with a massive pre-informed map of the world and motor control techniques.
Precisely. RLFP systematically overcomes this by infusing abstract knowledge structures, we call them priors, derived from existing vast foundation models into the RL loop. These priors, related to policy structure, value estimates, and success reward functions, they structure the learning space.
So it guides the learning process.
It dramatically improves sample efficiency and enables rapid, effective task resolution. For instance, algorithms guided by RLFP, like the Foundation-guided actor critic, use this prior knowledge to provide instantaneous, highly informative feedback. This effectively replaces the uninformative exploration and manual, costly reward engineering of vanilla RL.
It's a symbiotic relationship.
It is. High-level abstract knowledge guides physical experience, and that is vital for the rapid, structured skill acquisition needed in demanding fields like orthopedics, where time in the physical training loop is often the greatest constraint.
So we've covered the cognitive architecture and the intelligent data acquisition process. Now, let's talk about the physical manifestation. For systems performing precision surgery, the mechanics must be supremely dexterous and, above all, safe. Addressing the implementation side, what specific mechanical innovations are essential for ensuring physical dexterity and safety when robots work shoulder to shoulder with humans in a clinical setting?
The mechanical focus is shifting fundamentally away from purely rigid, heavy industrial machinery toward lightweight, adaptive designs, specifically soft robotics and biomimetics.
Drawing inspiration from nature.
Very much so. Researchers are drawing inspiration from compliant natural systems. Think organisms like the octopus or jellyfish, to use flexible materials like soft silicones, specialized hydrogels, and even liquid metals to create components that offer superior adaptability.
I understand the flexibility advantage for handling delicate instruments or manipulating fragile biological structures. But for orthopedic procedures, reaming, drilling, cutting bone, you need immense strength and rigidity. How do you reconcile soft materials with the required power and stiffness?
That's where the innovation in actuation or motor control becomes critical. The stiffness isn't abandoned, it becomes controllable. This is achieved through compliant actuation, most prominently with series elastic actuators, or SEEs.
Seize.
In any highly interactive robotic system, and surgical robots absolutely fall into this category, safety during close human-robot collaboration, or HRC, is non-negotiable. Rigid robots pose an inherent catastrophic risk of harm due to their high mechanical impedance.
They're just too stiff.
Exactly. CEAs fundamentally mitigate this by intentionally introducing a precision-engineered spring or elastic element in series with the motor.
And what's the functional outcome of inserting that spring into the drivetrain?
That compliance is transformational. It offers several benefits. First, it provides high force and torque fidelity because you can precisely measure the spring's deflection. Second, it provides low impedance, meaning the robot resists external forces less rigidly. And most importantly, it offers dramatically improved shock absorption.
I see.
So if an SEA-equipped surgical drill encounters unexpected chatter from the bone surface, or if the system experiences a sudden micro-movement from the patient, the compliance absorbs that transient impact force. This prevents force transmission spikes that could otherwise lead to injury or tool damage, and it fundamentally adheres to stringent safety standards like ISATS 15066 for close collaboration.
So the mechanics are being engineered for safety from the ground up.
The shift to CAs acknowledges that the physical robustness and safety of EAI is often constrained less by the algorithms and more by the mechanical engineering's ability to safely mediate that interaction.
The technical foundation is clearly robust, combining cognitive systems, compliant mechanics, and large-scale informed data collection. Now, let's pivot explicitly to our medical audience and address the immediate question. Where is this convergence of AI, advanced software, and new hardware already making an impact? Or where is it forecasted to change orthopedic and general clinical practice most profoundly?
We see the impact consolidating across two major streams: enhancing precision clinical care and optimizing operational efficiency to alleviate staff burden.
Let's start with the clinical side.
The most visible and high-value application remains surgical assistance and precision. We are already familiar with existing robotic platforms, of course, but EAI represents a profound shift. Current systems largely execute preoperative plans with minimal real-time adaptation. EAI moves to true adaptive cognitive control.
So what does a cognitive surgical robot actually do differently in the theater?
It adapts dynamically and continuously. The DPT-8 architecture enables surgical robots to use the world model to instantly validate every micromotion against physics. So if a surgeon encounters unanticipated scar tissue or rapid fluid shifts that obscure the visual field,
The robot can adjust.
the EAI system, using its FCMA-enhanced perception and world model, can dynamically adjust the tool trajectory, the force feedback, and the approach angle in milliseconds. It moves beyond fixed paths to genuine adaptive planning based on real-time nuanced sensor feedback, incorporating semantic reasoning from the MLLM on how to safely navigate the newly perceived anatomy.
That ability to adapt to fluid changes is key to maintaining consistency, isn't it? Regardless of the complexity of the case, what about the non-execution phases of surgery, like planning or training?
EAI is revolutionizing the preparatory phase as well. For preoperative planning, the world model allows for the integration of patient-specific biomechanical data. The system can simulate the stresses and strains on an implant or a bone graft before surgery, not just based on static models, but dynamically validating the plan through millions of simulated interactions informed by the patient's specific bone density, alignment, and expected tissue properties.
And for training.
In surgical training and proctoring, EAI systems can provide adaptive, real-time feedback to trainees. They can simulate realistic physical resistance and dynamically adjust the training environment's difficulty based on the trainee's performance and physiological cues. This has the potential to dramatically shorten the learning curve for complex orthopedic procedures.
Moving outside the operating theater, where else are we seeing physical intelligence deployed?
A huge growth area is in rehabilitation and prosthetics. Intelligent prosthetics with EAI capabilities are moving past simple motor control. They now incorporate sophisticated sensor suites that continuously monitor the limb's movement, external terrain, and internal cues like the user's muscle fatigue via EMG signals.
So the prosthetic understands context.
It does. The EAI system uses its world model to predict the user's intent and the necessary gait adjustment instantly. For example, a prosthetic limb can recognize a subtle transition from a rough pavement to a slick hospital floor and instantaneously adjust the foot placement, knee flexion, and ankle torque to maintain stability, significantly reducing fall risk.
That dynamic adaptability translates directly into higher quality of life and safety for the user.
Absolutely. And similarly, in smart rehabilitation devices, EAI systems can dynamically adjust resistance and therapeutic movement based on the patient's real-time functional performance, ensuring the optimal recovery pace without risking re-injury. The system acts as a highly attentive, tireless physiotherapist, individualizing every single session based on objective physical metrics.
And what about the less glamorous, but perhaps equally vital, applications in hospital operations that free up valuable clinical staff time?
Those support roles are transforming the daily workflow for every member of staff. EAI systems are rapidly assuming logistics and support functions.
What kind of things?
This includes complex, autonomous agents delivering pharmaceuticals, navigating crowded corridors to transport sterile equipment and samples, and managing hospital inventory. Using their enhanced perception and planning capabilities, these bots can interface seamlessly with complex hospital infrastructure, managing elevator use, door access, and dynamic routing around bottlenecks.
And what's the direct benefit to the clinician?
The primary benefit is efficiency and focus. By automating these high-volume, routine logistical functions, we are strategically freeing up highly trained human staff nurses, orderlies, technicians, and even surgeons to focus their limited time and expertise entirely on high-level patient care and complex clinical tasks.
The economic driver must be huge.
It's massive, and it underscores the necessity of EAI. The global embodied AI and robotics market is projected to soar from approximately $4.4 billion in 2025 to over $23 billion by 2030, driven significantly by the urgent demand for automated support in high-cost, labor-constrained sectors like healthcare.
The ultimate vision, as you've pointed out, is not replacement, but partnership, human-robot collaboration, or HRC. How does EAI truly function as a partner, as a productivity multiplier, in practice?
This alignment with the principles of what's being called Industry 5.0 is crucial for gaining professional trust. An EAI agent is designed to anticipate needs.
How?
In the operating theater, the system can monitor the surgeon's eye movements, hand positions, and the sequence of previously executed steps. It cross-references this observational data with its world model of the optimal surgical procedure. This allows the EAI assistant to anticipate the surgeon's next instrument request or dynamically adjust the tension on a tissue retractor milliseconds before the human operator even consciously registers the need for change.
So it's not just executing commands, it's preemptively enhancing the human operator's consistency and skill based on pattern recognition.
Exactly. The agent refines its internal action policies by observing and learning from expert human behavior, creating a collaborative environment where human intuition and critical problem-solving meet the robot's superhuman precision and endurance. It creates a seamless feedback loop that elevates the collective skill level of the team.
For EAI to achieve that deep integration we've just discussed, particularly in orthopedics, where the consequences of failure are so immediate, the bar for safety and trustworthiness is exceptionally high.
It has to be.
We are moving from software errors that might corrupt data to physical failures that could cause direct patient harm. So what are the most significant safety risks unique to physically embodied systems in a hospital environment? And what architectural safeguards are being implemented to counter them proactively?
This area really defines the future trajectory of EAI adoption. The risks are unique because they involve physical interaction. We categorize them into two essential groups: endogenous failures, those originating from internal system faults, and exogenous failures, those resulting from environmental interaction or malicious external attack.
Let's start internally. Beyond simple software bugs, what are the intrinsic hardware or systemic failures that medical professionals need to be acutely aware of when working with EAI systems?
Endogenous risks involve the inherent wear and tear and eventual failure of physical components. We've observed this for decades. Real-world examples exist. Mechanical malfunctions in existing, highly sophisticated surgical robots, such as components within the Da Vinci surgical system, have occasionally resulted in emergency conversions to open surgery, extended procedure times, or rarely physical complications.
And that's often related to things like actuator fatigue or sensor drift.
Yes, or unexpected power loss, or fundamental design flaws in the control system's response to unusual input states.
So how are researchers trying to mitigate these unavoidable mechanical risks?
Mitigation involves robust self-monitoring. Modern EAI architectures are being equipped with dedicated internal world models focused solely on the robot's own health. These systems use predictive maintenance algorithms to monitor subtle changes in motor currents, joint temperatures, and vibration signatures, allowing the system to flag potential component fatigue or drift before it leads to a critical failure.
The EAI predicting its own failure modes.
It's a necessary internal safeguard.
Now for the external risks. This is where EAI's physical presence creates unique, exploitable vulnerabilities that are completely different from those affecting purely software systems.
Indeed, exogenous risks are complex because they involve manipulating the robot's perception of reality to induce a physical failure. The first major category is sensor spoofing attacks.
So actively trying to fool the robot's senses.
Exactly. A deployed agent relies on precise, continuous sensor data, GPS, LiDAR, radar, IMUs for navigation and precision control. If an attacker can inject falsified or malicious data into this sensor pipeline, they can severely compromise the system's physical integrity and decision-making.
Can you give us some specific, clinically relevant examples of spoofing?
Well, take hospital logistics robots. If they rely on GPS for autonomous outdoor transit between buildings, GPS spoofing can mislead navigation, causing the robot to veer off its programmed path, potentially causing collisions or missed deliveries of critical supplies.
And in the surgical theater.
Consider the use of LiDAR or radar for collision avoidance. An attacker could tamper with those signals, perhaps causing the robot to erase a critical object, like a piece of patient monitoring equipment, from its perception map, leading to a collision. Or conversely, they could fabricate obstacles, causing the robot to halt a time-sensitive procedure unnecessarily.
And IMUs, the inertial measurement units, which are vital for maintaining the stability and tremor dampening required for microsurgery, they seem like a particularly concerning target.
They are. IMU spoofing, where the acceleration, velocity, or orientation data is manipulated, can be devastating. In microsurgery or procedures requiring precise instrument positioning, the robot relies on IMUs to compensate for the slightest tremor or micro-movement. Manipulating this data can cause an immediate, catastrophic loss of fine control, leading the robot arm to destabilize, potentially causing injury.
And there are other kinds of attacks.
We must also consider adversarial attacks, where imperceptible perturbations, often introduced via the light spectrum, like infrared light invisible to humans, can deceive the deep learning models. This could cause the system to misclassify a critical surgical instrument as a harmless piece of padding, or fabricate the presence of an anatomical landmark that simply isn't there, leading to erroneous and dangerous decisions during the procedure.
That seems like a direct pathway to physical catastrophe unless the cognitive core itself is fortified. Let's go back to the MLLM. We noted its propensity for hallucination due to a lack of grounding. In a safety context, how is that instruction misinterpretation being proactively locked down?
The risk of instruction misinterpretation requires a layered defense, starting with the proactive governance we discussed. While LLMs are powerful planners, their detachment from physical reality necessitates robust external affordance models. The system's intrinsic knowledge of physical constraints and value functions for grounding the MLLM's output.
So it's another reality check.
Yes. If the MLLM suggests a complex sequence of actions, the system must check not just the semantic logic, but whether the required force vectors or joint angles are physically achievable by the robot's body without exceeding safety limits.
And this is where the robot constitution comes back into play, but applied to ongoing behavior, not just training data generation.
Precisely. The prompt-based constitution is a crucial architectural component for ensuring that high-level natural language instructions are continually critiqued and refined towards safer, completer behavior. It acts as an immediate override filter that reinforces predetermined safety mandates. Its role in mitigating LLM-generated hallucination during physical task planning is vital.
It ensures the system only pursues paths that are physically and operationally safe within the hospital context.
Yes.
Beyond the internal cognitive safeguards, what about ensuring accountability and managing foreseeable risk in the actual physical space where humans and robots are co-located?
Controllability and human oversight are managed through increasingly sophisticated spatial methods. Frameworks like the Safer Architecture use dedicated LLMs exclusively for safety verification of the entire action plan before execution begins. But in the dynamic, shared workspace of a hospital, especially during collaboration, we rely heavily on advanced technologies like dynamic safety zoning.
Tell us more about dynamic safety zoning. Is this a physical boundary or a virtual one?
It's a dynamic virtual boundary that is often made visible. Systems like PRU use cameras and projectors to dynamically display and adjust visible warning and protective fields around the robot.
So it projects a sort of bubble of light on the floor.
It can, yes. These zones are not static. They continuously change size and location based on the robot's current status, its intended movement trajectory, its velocity, and the proximity of human personnel.
So the robot is projecting its invisible safety bubble onto the floor or the patient, showing the human team exactly where the safe working envelope is at that precise moment.
Exactly. And by using high-speed cameras to recognize human encroachment, even a misplaced hand or finger, the system can rapidly halt or slow its motion to maintain the smallest possible safe distance between the human and the agent, rigorously adhering to standards like ISOT's BODFU 066.
So you can collaborate very closely without needing bulky physical barriers.
That's the idea. The overarching goal across all these architectural mandates, from constitutional rules to dynamic zoning, is to achieve what we call Level 5 verifiability proactive, formal governance through architectural mandates, before widespread, complex integration takes place in the clinical environment.
And what does that mean in simple terms?
It means being able to formally prove, before deployment, that the system will adhere to its safety specifications under all foreseeable operating conditions.
This has been a monumental exploration into the inner workings and safety mechanisms of embodied AI. Let's synthesize this complex picture for our clinical audience. The core takeaway seems to be that EAI is not merely a better robot.
Not at all.
It is the fundamental integration of high-level abstract reasoning provided by world models and MLLMs with a resilient, compliant physical presence, which is enabled by innovations like soft robotics and series elastic actuators. This convergence is what delivers real-world autonomy and dexterity, with massive implications for advancing consistency and skill across medicine.
Absolutely. The transition means we are moving towards systems that can perceive, understand, and act with nuance in real time, adapting instantly to the dynamic, variable, and often chaotic nature of the clinical environment, whether that's performing a complex spinal fusion or managing critical logistical workflows.
If we look forward, beyond the immediate technical challenges of data scaling and hardware robustness, what is the core philosophical commitment that defines the future success and acceptance of embodied AI in healthcare?
I think the ultimate success relies on addressing not just computational and mechanical complexity, but the ethical and societal challenges related to trust and transparency. The future of EAI must be defined by two words: collaborative and governed.
What does that mean in practice?
It involves establishing clear standards for explainable EAI, allowing clinicians to understand why a decision was made. It means ensuring accountability and robust liability frameworks, and fundamentally fostering human-robot collaboration. We must ensure these agents function as transparent partners and productivity multipliers, strategically enhancing human performance rather than serving as black box replacements.
That emphasis on transparency and partnership will be what truly unlocks the potential of EAI in high-trust sectors like orthopedics.
Indeed. And for those of you navigating this rapid technological change in your professional context, collective understanding is key to navigating this future. If you found this deep dive valuable, please consider rating and sharing the episode within your professional network.
A perfect point. Finally, give us one final provocative thought to leave our listeners with, a concept for them to mull over as they consider this integrated future.
If you reflect on the underlying architecture, the shared backbones of these new systems, the multi-policy shared architectures like ChatVLA, we realize something quite profound about learning.
Go on.
Because the core foundational models are the same, a surgical robot's next great insight into fluid, safe motion, and precise force application might not originate from a tightly controlled cleanroom experiment focused on bone cutting. Instead, it could come from the anonymized experience gathered by a hospital logistics bot learning to safely and efficiently navigate dynamic, crowded corridors while avoiding collisions with people, equipment, and walls.
So the systems are learning from each other's experiences.
Yes. So how does this interconnected learning, where the high-stakes, low-volume procedures are dynamically informed by the low-stakes, high-volume logistics tasks, fundamentally change our entire view of expertise, of skill transfer, and the necessary boundaries between disciplines?
That is a fascinating concept. Intelligence harvested from the hospital ecosystem itself, unifying previously disparate functions under a single cognitive umbrella. Professor, thank you for guiding us through this extensive deep dive into the new frontier of embodied AI in healthcare.
My pleasure.
That was Deep Dive Ortho, and we'll be back next time with more essential insights.